Okay, so today we are going to learn a very important and useful tool which will allow us to prove many identities just for in a routine way. This is called hypergeometric series. So we will introduce several notations. They may look a little complicated, but once you get used to it, this is very easy to use. It's just a routine. So please don't be intimidated by its looking. So what's the definition? A hypergeometric series is a series, infinite series like this, such that the ratio of the consecutive coefficients is a rational function of n. So there are many useful functions of hypergeometric series. So for instance, geometric series is of course a simple form of a hypergeometric series. So the geometric series 1 plus x squared ... It is a hypergeometric series because the ratio is always 1, and 1 is a function of n, which is constant, the rational function. So this is trivial, probably the simplest hypergeometric series, and because it is a generalization of geometric series, this is the reason why it's called hypergeometric series. And also exponential function. This is 1 over n factorial x to the n. This is also hypergeometric series. The an plus 1 over an. This is This is 1 over n plus 1 factorial, 1 over n factorial. So it's 1 over n plus 1. It is a rational function in n. So it's also a hypergeometric series. Okay, and there is a standard way to write a hypergeometric series. This is the well-known notation. We can write, because it is a rational function, we can factor the numerator and denominator. The numerator and the denominator are polynomials in n, so we can write in this way: a1 plus n, a2 plus n, ar plus n, and b1 plus n. We just factor the numerator and the denominator. And for some reason, we will include 1 plus n in the denominator always, times constant. If there is no factor like this, we can multiply both the numerator and denominator so that we have always this factor there. This is a constant. A's, B's, and C are constant. And then Fn can be written. So initially f0, and then we keep multiplying this. So it's going to be f0. Okay. So what is f1 then? So f0 over f1 equals a1 ... ar b1 ... bs times 1 times c. Okay. So f1 is a1 ... ar b1 bs times 1c times f0. What is f2? Similarly, it's a1 plus 1, ar plus 1, b1 plus 1, bs plus 1 times 2 times c times f1, etc. So we now replace f1 by this, and in general Fn can be written in this way. Fn equals F0 times A. I'm going to use this notation. A R B S n factorial C to the n. Here, A sub n is by definition A times A plus 1 times A plus n minus 1. So this is called our rising factorial, or this is sometimes called a rising factorial, or also called a Park-Hammer symbol. This will be used very often in this lecture, especially today. If you apply this relation n times, then you will get this. Okay. So hypergeometric series can be written, or can always be written in this way. The nth coefficient is of this form. Okay. So then we can write down hypergeometric series in a standard form. So that here is the notation. RFS A1 dot 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 AR B1 dot 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 BS semicolon Z. This is also written in these two rows, A1 AR B1 BS semicolon Z. They are the same, and definition is n from 0, A1 sub n, AR sub n, B1 sub n, BS sub n, and n factorial, Z to the n. So in the numerator we have Park-Hammer symbols with using the numbers in the first row. The denominator we have the product of the Park-Hammer symbols with the numbers in the second row, and we have n factorial. You don't want to forget this, all right? So you can think of a hypergeometric series as something like this, and this is always, the constant term is always 1, so hypergeometric series will be a constant multiple of RFS. All right? So, example, the geometric series is what? Here, we need to write this, the coefficient, in this form. But there is no n factorial in the denominator, so we multiply n factorial. But this is the same as 1 sub n, because this is 1 times 2 times dot 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 up to n. So they are the same. So Zn. Now this is of this form. So we have one. By the way, R means the number of factors in the first row. S is the number of factors in the denominator except this. So we have one thing here, so it's 1 F. We have nothing here, so 1 F0. And in the numerator we have 1 0. Because there's nothing there, we just write like this. It means nothing there. And Z. So this is the geometric series can be written as a hypergeometric notation like this. Okay? And what about e to the z? This is n z to the n factorial. Now this is already of this form. Only we have nothing in the numerator and the denominator. So it's 0, f0, nothing, nothing, z. All right? And more log function. This it has an expansion like this. z to the n over n. Now let's see how we can turn this into this form. So first, let's factor z out, z. And this is the same as this. First, we replace n by n plus 1, then n goes from 0, and then I just factored z out. Okay. Now, how can we make this in this form? Okay. So let's try to multiply here, because we need n factorial, n plus 1. Let's write n factorial twice. I mean n factorial squared. Then we get n plus 1 factorial, n factorial here, n factorial, and z to the n. Okay. Now these are can be written that way. N factorial is 1 sub n. Here 1 sub n. What is n plus 1 factorial? As a Parkheimer symbol. Can you write this as a Parkheimer symbol? It's going to be 2 sub n, right? Because 2 times 3 times dot dot dot, n plus 1 is 2 sub n. This turns into this, and now n factorial. So now this is 2f z times 2f1. We have 1, 1 in the top, 2 below z. The log function can be written in terms of the hypergeometric. This kind of thing is, there are several things that you need to remember, but if you use those things, it is quite routine to translate a series in terms of a hypergeometric series, and it's very you don't really need any clever idea to do this. Just you apply what needs to be applied. Okay, so let's do one more example. Cosine. It is minus 1 to n, z to 2n over 2n factorial. Now, how can we change this into a hypergeometric series? Okay, let's rewrite this. Minus 1 to n. Let's combine these two together. Then minus z squared raised to n, right? And here, I'm going to separate this into like this. 1, 3, dot, 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 2n minus 1 times 2, 4, dot, 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 2n. Because we want n things multiplied instead of 2n things. So I just separate that like that. Now, what's next? Here, okay. Let's see what happens if we consider this. What is this? We want to write this as a Parkheimer symbol. So we increase something, we multiply something times, say a plus 1 times a plus 2, etc. But here, these are increased by 2 at a time. So we can, but this can be considered as like this. And then 2 to the n, right? I just divide this by 2 and then multiply by 2. Now, these are increased by 1 at a time, right? So it's going to be 2 to the n first, and 1 over 2 sub n. So it is can be written in this way. We want something like this, something raised to n and Parkheimer symbol. This is good. And the 2 times 4, this is easier. 2n. It can factor this out, and then n factorial, and of course this is like this. Okay? Now we just need to replace this over there. And this part is 2 to the n, 1 over 2 sub n. This part, 2 to the n, 1 to the n. Now finally we combine some the factors of a power of n. Then 1 over, and this is what? Just n factorial, right? So yeah, actually this is not really necessary. But 1 over 2 sub n, n factorial, and minus z squared over 4 to the n. Okay? And now, what is this? There's nothing on the top, so 0. There's one thing here, so it's 1. So nothing, and 1 over 2 minus z squared over 4. So cosine is also a hypergeometric series. Now what about sine? By the same idea, you can check that sine is z times 0 f1, nothing, 3 over 2 minus z squared over 4. So by the same idea, you can check this. Any question so far? So we have seen several hypergeometric series, and turns out that many useful series are hypergeometric series. And this is very useful because hypergeometric series, there is a different ways of writing series. Because they are the same, they are all the same. But hypergeometric series is in some sense a standard way to write a series. So it is easy to identify whether this series is something or not. So this gives us a kind of standard way. So what is the so this is the basic idea how we prove a certain identity. It's very simple. So suppose we want to show an identity. So when you are working on some problems, they might turn out to be just showing one identity. Then you want to show this, and this is the way you show using hypergeometric series. First, you express things in hypergeometric notation. Express one side. So identity is something like this. Summation of something equals a single term, like that. Suppose you want to show that like that. So then express one side, the left-hand side, which is a sum, as a hypergeometric series. Hypergeometric series. So like this. Try to write this as a RF as something like that. And then there is a list of hypergeometric identities. So look up. It's like you look up integration table if you want to integrate something. Look up a suitable formula for the expression, hypergeometric expression that you just obtained in the first step. And that's it. That gives you the formula. So you change this into a hypergeometric notation, and then you look up some suitable formula, and if you find one, then that immediately gives you that this is equal to something, and that's basically the proof. Very simple. This is so simple and routine that it can be programmed. Then you don't really need to do anything. Just computer can prove this without any clever idea. So maybe you don't really need to learn this because computer can do this for you. But it is important to understand the idea behind this. because you know you use calculator, but you need to understand how it works if you really want to be a want to understand mathematics. So let's try how we do this. Let's show that this is very simple and well-known identity. Everyone knows how to prove this here. The sum of the binomial coefficients is equal to 2 to the n. There are many proofs of this, but we want to prove this using hypergeometric trees. Just applying this. Okay, so proof. So step 1, let's consider step 1. So we need to express this, the left-hand side, as a hypergeometric series. So, and choose I. So let's write this in a different way. This is what? N times n minus 1 dot 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 n minus I plus 1 over I factorial. Okay, this is binomial coefficient, so it looks like that. Okay, so what is this? Can you write this as a Parker-Hammer symbol? Yeah, if you think of this, then you increase number by 1 at a time in this way, right? So you may want to try to write this as 1 minus I plus 1 sub I. This is okay. They are the same, but this is not what we want, because we want this to be a constant with respect to the summation index. This is correct, but this is not what we want. So we want constant here. How can we do that? This is constant. The only problem here is that it is decreased by 1 instead of increased by 1. But we can fix this by multiplying minus 1 there. Okay? So n minus 1 dot 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 n minus I plus 1. This you multiply minus 1 and multiply minus 1 again, then we get, there are I factors like that, minus n plus 1, minus n plus I minus 1. They are the same. Now, it is increased by 1 at a time, so this is constant, minus 1 to I, minus n sub I. This is a good thing for us. So, what is that? This I from 1, I 0, I factorial minus 1 to I minus n sub I. Now this is already a hypergeometric notation form, right? We have one thing here, nothing here, so it's 1 f0, not minus n, and nothing, and z is minus 1 in this case. Okay, so we expressed this as a hypergeometric series. So the first step is done. All right. Now we need to look up a table, and there is a formula like this. Look up the table, which I didn't really give you yet, but then you will find something like this. There is an identity in the list of hypergeometric identities. This is equal to 1 minus x to raised minus a. There is an identity like this in the list. So you will use this kind of thing very often. Now all you need to do is to substitute the numbers here. Then 1f0 minus n, nothing, minus 1. Here a equals minus n, x equals minus 1. So it's 1 plus 1 here. And this is n. So it's 2 to the n. That's the proof. That's the end of the proof. Very simple. Okay. Any question about this? This is probably one of the simplest proof, I mean, using hypergeometric series, but the idea is like this. Sometimes identities can be more complicated, but the idea is exactly the same. You express this as a hypergeometric series and look up the table, set up a formula, and done. So if you took a class like discrete math or combinatorics, you have seen many identities using binomial coefficient. They are, in this way, kind of trivial to prove. They can all be proved like this. So very, very powerful. So now whenever you meet a binomial identity involving binomial coefficient, you can try this kind of idea. All right? So let's see one more thing. Another well-known identity. So this is called Vandermonde identity. There are, of course, many proofs, combinatorial proofs as well. But we will try to prove this using hypergeometric series. So proof. The first step, write this as a hypergeometric notation. All right, so binomial coefficients, we already expressed this as a hypergeometric series, right? We already expressed this like minus a sub I factorial. Okay? And what about this? K minus I. If you substitute b by a, k minus I by I, they try to use this, then that's not what we want, because this will not be a constant, or this is not constant. Okay, so let's try to express this. So first use the formula for the binomial coefficient, so b minus k plus I. Okay? Now we're going to work on each factor and then factorial. Try to write that as a Parkheimer symbol. Okay? K minus I factorial, what is that? We already did that, if you remember. This is minus 1 to I minus k sub I. This is like that. Okay? We already did that. We factor minus 1 out, and then that's basically it. Oh, no, it's not. Sorry about that. Let's do this step by step. Oh yeah, that's not. So the idea here is that, okay. Just assume that this is k factorial, but of course they are not. There are more factors here, right? So we need to divide this by what? Divide this by k minus 1, k minus I plus 1, right? We need to divide this by I factors like that. Now we have to apply that thing. So k factorial, we factor minus 1 out. Yeah, I'm doing this one step at a step by step, but later I'm gonna just write this at once. This is now increased by 1, so it's k factorial minus 1 to k minus k raised sub I. Now everything is okay. Oh yeah, that's right. This is I. Okay, this is good. Now, what about this? B minus k plus I factorial. So it is a product of integers 1, 2, 3 up to b minus k plus I. So that is, first we have b minus k factorial, and then we have what? B minus k plus 1 dot 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 b minus k plus I. Here there are I factors, and increased by 1 at a time. So this is b minus k factorial b minus k plus 1 sub I. Okay? So now everything is in a good Park-Lemma symbol. So finally, b sub k minus I, b choose k minus I equals, here b factorial over this is equal to this. So it's k factorial, I'm going to move this in the numerator, minus 1 raised to I minus k sub I. Okay? Now this is equal to this. So b minus k factorial, this b minus k plus 1 I. Okay? Now if you look at this part, they are constant with respect to I, summation index I. This is just a b choose k. So the left hand side here, oh yeah, actually this is just for this. So now everything in one place. Minus 1. Oh, here again I. Minus 1 raised to I minus a I factorial. In this part, I wrote that down over here. So let's forget about this and then multiply b choose k. So the red part here is b choose k. So here minus 1 raised to I minus k sub I b minus k plus 1 I. Okay. We can cancel this. So what is that? So b choose k. And we have two things and the one thing below. 2f1 minus a minus k b minus k plus 1 and 1. So the first step is done. The next step, there is lookup, and then you will find like this: 2f1 minus n b c 1 is equal to c minus b sub n c sub n. This is a general identity, and you will find this in the table. Oh, now we just substitute the numbers. Oh yeah, we need more space. So what's the left hand side? So left hand side here, left hand side equals the b sub k, and then here a, okay, let's see. Okay, doesn't really matter, but I'm going to use K and A like that. K, A. You can change this, and this will change it a little bit. They will give you the same answer, but yeah, I'm going to use this just to be consistent with my lecture note. All right. So C, what is C? B minus K plus 1. What is B? Minus A. So here, B minus K plus 1 minus A. So it's plus. So A plus, okay. A plus B plus 1 minus K sub K. All right? This is nothing but substitution. And here C sub n, c sub k. So c is b minus k plus 1 sub k. Okay. Now it's just cancellations. It's b factorial, k factorial, b minus k factorial, and what is this? So here, so if you think of this, this is a plus b plus 1 plus k, and then a plus b plus 2 plus k, up to a plus b, right? So it's going to be a plus b sub a plus b factorial, a plus b minus k factorial. This is for the numerator. Okay? If you cancel the common factors, then you will end up getting this. What about this? Again, this is b factorial divided by b minus k factorial. Okay? You can, if you can't cancel the common factors, you will get this. Now, you just need to cancel this and this, and what? This is binomial coefficient a plus b, choose k. So that's the proof. Any question? So this is more complicated than before, but the idea is the same. So hypergeometric identities like this, it's kind of messy. You need to do many computation, but they are all kind of straightforward. So if you practice this many times, then this will be very simple for you. All you need is just time and patience. At the end, you will get an identity for free. All right, so this is hypergeometric series. Now, there is a Q version of this, and it's called basic hypergeometric series. So it has this adjective, basic, but doesn't mean that it's simpler than hypergeometric series. This is in fact more complicated than hypergeometric series because there is Q. It's Q version. So definition. Definition is similar. A basic hypergeometric series is a series like that, such that the ratio of the consecutive coefficients is a rational function of, so if I write n, then it's a hypergeometric series. The basic hypergeometric series is a rational function of q to the n. So, in other words, fn plus 1 over fn equals, if you factor the numerator and the denominator, and because it's a polynomial, you can factor this as a linear product of linear factors, 1 minus a1 q to the n. You can write like that. Because we may have some, so these are like, we just factor the polynomial as a linear factor. So we may have something like this, because they correspond to non-zero roots, and this will correspond to 0 roots. Times C. Okay? But for some reason, we will assume that T is, so without loss of generality, we assume that T is what? 1 plus S minus R. Because we can just throw in more factors there and there by assuming that Bs equals 0, then it doesn't really matter. So we will consider this thing. In other words, like this part is determined by the number of factors above and below. Yeah. If you need, then you just you can add more terms like this, right? Then you can change the R and S. Okay, so we will assume this, and then with f, the constant term being 0, if you assume that, then this can be written in this as before. We can write this, the basic hypergeometric series. If you apply this n times, then you get a formula for Fn in terms of F0 and these things. Then in general, you can write A1, AR, Qn. Oh, sorry that I forgot something here. Like before, we had 1 plus n, like n. We always have n factorial in the numerator. We have similar thing. So it's 1 minus q to the n plus 1. We will always have something like that in the denominator. So this will give us q factorial, q sub n. And this will give us okay, and also for some reason we will assume that we have minus here. Then minus 1 to n, q to the n choose 2, 1 plus s minus r, z to n. Okay, this look a little complicated, but this is the way it is. So we will have a cube. This is a standard form for a basic hypergeometric series. Here, the notation here, I'm not sure if I introduced this before, but yeah. This is 1 minus a times 1 minus aq, 1 minus aq to the n minus 1. And we also consider n being infinity, then this is just infinite product with no n. And for simplicity, we will write things like that. This will be a product of n things, just for shorthand of this. All right? So these are common notation. So this is called Q Park-Hammer symbol. So this will be used very often in Q series, so you need to remember this. And this will be denoted by, this is denoted by R phi S A1 AR B1 BS Q and Z. So Q specifies this. Q is normally called the base Q. So this is the standard notation for a basic hypergeometric series. So these notations are things that you need to remember. Okay. So this part is kind of looks a little ugly than other things, but mostly we will be dealing with R equals S plus 1 case. So this number is 1 bigger than this. In that case, this just becomes 0, so this goes away. All right? So in general, it looks like this, but mostly we will be dealing with this case. So in other words, in particular, if R equals S plus 1, then S plus 1 be S A1 A S plus 1 B1 BS QZ is equal to summation n from 1 using the previous notation A1 A S plus 1 Q n. Here the QQ sub n is kind of hidden, so you need to have that. Zn. So in this case, we don't have that strange factor. You don't forget to write this as well, Q. So in some sense, they are balanced. There are n factors, or S plus 1 factors in the numerator, and plus 1 factors in the denominator. So like if they have the same number of factors, then you have a nicer expression like this. We'll be mostly dealing with this. Okay, so what is the connection between Q hypergeometric series and hypergeometric series? So hypergeometric series is a special case, can be obtained as a special case of basic hypergeometric series. So note that limit n approaches 1, Q approaches 1, 1 to minus Q raised to A, 1 minus Q. This, you can see that this is just A. You can factor this out and divide this and you get that. And limit, therefore, limit Q approaches 1, Q to A, Q n, 1 minus Q to n. This is equal to A sub n, Parker-Hammer symbol like that. Because this is 1 minus Q to the A, 1 minus Q to the A plus 1, 1 minus Q to the A plus n minus 1. And then we have one factor 1 minus Q for each factor here. So if you apply this, then you get A plus 1, dot, 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 A plus n minus 1, which is exactly this thing. So proposition, this is connection between basic hypergeometric series and hypergeometric series. RVS Q to the A1, Q to the AR, again, if R is S plus 1, you can forget about this thing. This is equal to RFS A1 AR B1 BS and Z. So if you have an identity for a basic hypergeometric series, then you can, by using this, you get identity for hypergeometric series. The proof is just simple, so I'm not going to do that. Any question? Okay, then we will take a short break and resume at 10 o'clock.